Hello, Chemistry of Earth and Space Science students. Today we're looking at Unit 4, Lesson number 4, which is about significant figures and dimensional analysis. The dimensional analysis video will come after this one. So objective for this particular lesson is to identify how many significant figures there are in a measurement by using our significant figure rules, and to express measurements to the correct degree of precision. And then also to correctly express the result of a calculation with the correct number of sig figs. Some of your classes, physics especially, may have introduced the concept of significant figures, and I know they can be pretty confusing, but you have to trust me on that there's a purpose to why we use significant figures. So the key question to come out of this is, what are significant figures and why do we use them? And how do we use them in calculations? So here's an example. If I were to try to calculate the density of an object like we did in the lab earlier on, where we calculated the density, and density being mass divided by volume, and we had these values for those densities, for those masses and volumes, one thing we could have done was to take and figure what the volume of the rock was, and then to use our density calculation by taking the mass divided by the volume. Now I gave you the mass, 120.56 grams and 27.7 milliliters. I put those in my calculator and I get this answer. And the question would be, that I often get even from you guys, is how do you want me to round this? Do you want me to go 1 digit past the decimal, 2, 3? How do you want me to round this? Well, believe it or not, there's a right way to do it using what's called significant figures. So let's start at the beginning. With any measurement you take, including ones that are on electronic devices, that value is not 100% perfect. There's always some degree of uncertainty to that measurement. So let's look at this. So here I have a graduated cylinder, and the graduated cylinder has some water in it, and I can tell, so I can use my cursor, I can tell that this graduated cylinder has somewhere between 25 and 26 mils. Because there's my 25 mark, there's my 26 mark. And if I wanted to measure that, I'd look at where that meniscus is relative to those two lines, and I might say it's 25.8 mils. Okay, I am absolutely sure it's 25 point something, and I am estimating one more digit. I might even go so far as to say, looking at this one's between, was it 24 and 25? As a matter of fact, it looks like it's exactly on the 24. I think that meniscus is touching the line, so I'd say that was 24.0 mils. But again, I am sure it's 24, and I am saying in my judgment that that meniscus is on the line. So I am certain of the 2 and the 4. I'm kind of using my estimating powers to determine what the last digit is. So I have certain digits, and I have ones I'm not certain of. I'm not 100% sure of. Every measuring device you're going to use has that type of precision to it, and that type of certainty to the values. So why is there uncertainty? Well, again, no instrument is perfect. They're all going to have some degree of certainty. So for instance, our balances in class go to 2 digits past the decimal. Our balances, one of the balances I use for AP Chem goes to 4 digits past the decimal. And when I was in college, we had a couple of them that went to 5 digits past the decimal. With each one of those tools, the precision, or better yet, the certainty of the measurement was increased because of how many decimal places I could go out. Which one of these? So I got two balances here. Which one do you think can give the least certain value? Well, it's kind of a trick question because you got this cool thing on the left hand side that is like from a deli or a produce stand, and then the one on the right is electronic with little digital numbers. Obviously, the one on the right is going to be more precise, more certain, whatever number you get on that. Usually, those ones you use in the produce or in the grocery store, those are estimating. And then you put it up, take it up front, they measure it exactly on an electronic one, and you get an accurate measurement of the weight of whatever you have. So we use what are called significant digits or significant figures. The two terms, significant digit and significant figures, are used interchangeably. So what you're looking at is in a measurement, the digits, the numbers, that show how precise the measurement is. And it's always going to include digits you're certain of, plus the first estimated or the first uncertain digit, indicating how reliable that number is. I always say that if I take a book and I put it on one of our balances here, we might get a measurement of say they're probably about 220.25 grams. But if I were to put that on a scale that only went to the one spot, then you say 225, and that's it. You wouldn't have an actual value. You're just not that certain. Whereas the electronic, I've got a little more certainty as to what that number is going to be. I probably messed those numbers up, but you get the point. So, first things first. When looking at a measured value, a value that's given to you, you are going to first need to know how many significant digits or significant figures that particular measurement has. And there's a series of rules, and there are actually five different rules. So the first was easy. If you have a number and all of the digits are not zeros, as a matter of fact, if you have a number that has digits that have zeros, the ones that are not zeros are absolutely going to count as being significant. So if I were to say 3,456, that number has four stick figs. The 3, 4, the 5, and the 6 are all significant because all three of those are not zeros. That's easy. So I take care of 9 out of the 10 possible digits. What to do with those ding-dang zeros? Well, there's like a handful of rules for the zeros to make things that much more complicated. So it's the first zero rule. Leading zeros don't count as significant figures. Okay, so what's this leading zero look like? This number, 0.0486, has two leading zeros. 1, 2. Has two leading zeros. Those leading zeros are not significant. Now, I'm not going to say they're not important because they are important. The number of 0.46 is very different from 0.486. Okay, very different. But, so zero is important. This zero here is very important, but it's not significant when talking about measurements. So that number, 0.0486, has 3 significant digits. You may see some really extreme circumstances, like a number may be expressed as 0.125 pounds. That this zero is stupid. It's like, why would you start by putting a zero there? It just tells you that whatever tool you used could have measured up to the thousands place, but we didn't need to. It was only 125. So this only has 3 sig figs. What are the bad zeros? Captive zeros. So a captive zero is when a zero is in between two other significant digits. So for instance, 16.07, this digit here, this 0 here, is captured. It's between this significant digit, a non-zero, and this significant digit, a non-zero. So the value of 16.07 grams, that number, that value has 4 significant digits or 4 significant figures. Last thing about zeros, so you have them leading, you have them in the middle, captured, and then there'll be the trailing zeros. Trailing zeros are a little tricky. Trailing zeros are a little tricky. One way to look at this, I guess, for what we will be doing in our class is to say trailing zeros are only significant if the number has a decimal point. So for instance, 9.300 has a decimal point. So these trailing zeros, the ones that come after significant digits, they are significant. So that has 4 significant digit figures. If I had a number that say 1200, well, that would only have 2 significant digits, the 2 and the 1, because these zeros are trailing, but there is no decimal place. Guys, so kind of a weird little rule there. It's really saying, I always call these zeros the bragging zeros. You know the people who are in lab, they measure something and it's like, I got exactly 2.00 grams. It's like, great. So in my calculator, I'm still putting in 2, right? It doesn't really matter, but it does as far as the calculating piece, which is the second part of this PowerPoint. Now, some things to consider when doing significant digits, significant figures. If something is an exact number, a counted number or an exact number, a defined value, that has an unlimited number of significant digits. For instance, a meter is 1,000 millimeters. This number, 1,000, has an infinite number of significant digits. Why? Because it's a defined value. By definition, a meter is 1,000 millimeters, or 12 inches in a foot. This 12 has an unlimited number of sig figs because it's a defined value. I have 12 inches in a foot by definition. It's not 12.2. It's not about 12. It's exactly 12. So that means that has an unlimited number of significant digits. Now, there is one situation where it can kind of be a little ambiguous. Another way to say, you're not really sure how many digits, significant digits something has. So here's an example. Suppose you had the answer of 200 centimeters, but you need to express that as 3 sig figs because, again, we're going to talk about how to round and how to calculate in a little bit. But suppose you got the number in your calculator with 2,000 or 200 centimeters, and you needed to say, well, wait a second, I wanted that to be 200, but I want to express it as 3 significant figures. A couple different ways you can do that. One would be to put a decimal. See the decimal? Put a decimal there. That would make that significant all the way out to the decimal point. A much, 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 much better way to do it and more consistent way to do it is to use scientific notation. So 200 is 2.00 times 10 to the second. A bigger quandary would be, what if I had 200, but I want to have 2 significant figures? Well, I just can't put a decimal here because that changes the number. So that's not possible. I'm going to get rid of that dot because it kind of freaks me out. Okay, come on, go away. There you go. So what do? So one of the things we're going to do is make sure we write this in scientific notation. This would be 2.0 times 10 to the second, whatever the units are, centimeters in this case. This number has 2 sig figs. So my expression here has 2 significant digits. It's a much better way to not have to get kind of fancy with identifying the number of significant digits. It always happens when there's trailing zeros that some of them might be significant. Okay, so let's look at some practice. I'm going to go through these, and you can try them on your own because you have them on a sheet in front of you. If I had the number 1.0070 meters, that has how many sig figs? 5. 17.10 kilograms, that has how many sig figs? 4. 100,890, that has how many sig figs? That has 5. That last zero is not significant. It's a trailing zero, but there's no decimal in this number, the comma. What about 3.29 times 10 to the third seconds? Well, that's easy. 3.29, there's no zeros there. That's going to be 3 sig figs. What about this? 0.0054 centimeters. There's a much better way to express that number, but let's do it anyway. Well, we already know leading zeros are not significant, so that means this number only has 2 sig figs. Just those 2. And what about this? 3,200,000 millimeters. Well, those are all trailing zeros, but there's no decimal, so only the 3 and the 2 are significant. That only has 2 significant digits, just those 2. Okay, let's practice maybe rounding. Let's practice rounding. Let's look at a number that comes out of our calculator and practice how to round it. Let's try this one. If I got in my calculator, punched out 12.56, but I had expressed that number as 3 sig figs, I'm going to start at the beginning, 1, 2, 3. I'm going to look to the right, do 5 or above, give it a shove. In this situation, because it is above 5, I would bump that 5 up to a 6. Oops, they're all here. And get, I thought they were on the screen already. And get 12.6. What about 1.00 times 2 sig figs? Well, 1.00 has 3. If I lose this last digit 0, then it's got 2. What if I had 1,200 to 2 sig figs? Well, it already has 2 sig figs. 1,200 is 2 sig figs. What about 1,200 to 4 sig figs? Well, that's where I got to do the fanciness. I could do 12 dot, or I can do scientific notation of 1.200 times 10, that's a 10 to the third. Either or. What about 1,200 to only 3 sig figs? Well, I only have one choice how to do that. 1.20 times 10 to the, oops, I need to erase that because I got a little overzealous. 1.2 times 10 to the third. What is this? 0.00567, and I want to do it to 2 sig figs. So again, the logic is start first significant digit. That's this one. 1, 2. Look to the right, 5 or above, give it a shove. So I get 0.000, 5, 7. Last one, 1.2500 to 3 sig figs. I'll start at the first one. 1, 2, 3. Got to figure out what to do with the 5. Look to the right. 5 or above, give it a shove. It's not above 5. So it just becomes 1.25. So for the second part of this PowerPoint, it's going to be all about how to properly identify the number of sig figs, so you'll have to round when you're done. So the first handout in your packet was significant figure practice. You should be able to finish it with what we've just done. Let's move on. Mathematical operations. There are 2 sets. We're going to have one set of rules for multiply and divide, and one set of rules for addition and subtraction. And they are similar, but very different in how they do the rounding. So let's worry about multiplication and division first. In multiplication and division, the number of significant digits that you use, or that your result will have, is going to be equal to the number of sig figs in the least precise measurement, or a better way to put that is the measurement you're using in the calculation that has the least number of significant figures. Here's an example. 6.38, then I multiply times 2.0, and my calculator gives me 12.76. But since 2.0 has 2 sig figs, and 6.38 has 3 sig figs, the lower number between 2 and 3 is 2, so I have to round to 2 sig figs, which means this number simply becomes 13. Let's practice that. So I take a calculation and I want to do this. I put it in my calculator and it says this. First off, how many significant digits do we need to round to? Let's do a quick check. This one has 3. This one has 2. So I need to round to 2 sig figs. And that number rounded to 2 sig figs would be 23 meters squared. What if I wanted to do that density thing? Got 100 grams divided by 23.7 centimeters cubed. My calculator gives me this. Oh, wow, that's yucky. So this has 4. This has 3. The lesser number between 4 and 3 is 3. So I have to round my answer to 3 sig figs. And I get 4.22 grams per cubic centimeter. Next, 0.02 centimeters times 2.371 centimeters. And my calculator gives me this. Well, since this only has 1, and this has 4, I have to round this to 1 sig fig. So it becomes 0.05 centimeters squared. Keep going. 720 divided by 3. Let's see, 710 has 2 sig figs. 3.0 has 2 sig figs. So whatever the calculator gives me, I need to round to 2 sig figs. 1, 2. I got to figure out what to do with that. 3. I look to the right, I see that 6. I'm going to have to bump it up. So my answer expressed to only 2 sig figs would be 240 meters per second. A few more. 1,818.2 pounds times 3.23 feet to give you a foot pounds. And my calculator gives me this. So I look at this and I say this has 5. This has 3. I need to round to 3. So this answer becomes 5,870 feet pounds or foot pounds. 1.030 grams divided by 2.87 milliliters. 1.030 has 4. 2.87 has 3. So my final answer at a calculator is that. I now then need to round that to 3 significant figures. 1, 2, look at what to do with this 8. And it becomes 0.359 grams per milliliter. Okay, so you're looking for multiplication and division. You're looking for number of digits, and you're figuring out of the numbers you use in those multiplications and divisions, which number had the least number of significant digits. Okay, said there's 2 camps. There's multiplication and division and addition subtraction. So that's the addition subtraction. This one's a little harder because you have to kind of visualize it or take into account, especially if everything has decimal places. But the number of decimal places in the result equals the number of decimal places in the least precise measurement. Here's what I mean. If I take 6.8 and I were to add it to 11.934, my calculator gives me this. Well, this goes to the 1 digit past decimal. This one goes 3 digits past decimal. So I need to round this to the least number of decimal places, and that would be to where the 7 is, and that would be rounded to 18.7, and whatever the units are, that would have 3 sig figs. Notice it's not number of digits because this 6.8 had only, where's my cursor? 6.8 only had 2 sig figs, and this had 5, but my answer has 3. That's because we're talking about the location of the last sig fig. I call it the leftmost last. The location of this leftmost last sig fig. One of the last sig fig is the 8, and 6.8 is the one most towards the left. I'm going to round to that location, to the 1 digit past decimal. Let's try some. I type this in the calculator, 3.24 meters plus 7.0 meters. I get this, but since this has 1 digit past decimal, where this has 2, I'm going to round to only 1 digit past decimal. Notice I'm not doing numbers of digits. I'm looking at the location or the number of decimal places. How we take 100.0 grams, subtract from it 23.73 grams. So this goes to 1 digit past decimal. This goes to 2. So when I get my calculated value, I'm going to then round it to only 1 digit past the decimal. Figure out what to do with this 2. Look to the right, it's a 7, which means I'm going to have to bump it up. So I get 76.3 grams. Let's do a few more. 0.02 centimeters plus 2.371 centimeters. Well, this one goes to 2 digits past decimal. This one goes to 3. So when I get my calculation, it has 3 past the decimal, but I need to round it so that it only has 2. So that becomes 2.39 centimeters. Another one. 713.1 liters minus 3.872 liters. I get this. But now I need to round it. This goes to 1 digit past decimal. This one goes to 3. The least between 1 and 3 is 1. So I round it to 1 digit past decimal. And I figure out what to do with that 2. I look to the right. It's not greater than 5, so I'm going to go ahead and leave it. I get 207.9.2 liters. 118.2 pounds plus 3.37 pounds equals that number of pounds. But then I look at my values I used. This one only went 1 digit past the decimal. This one went 2. So I can only go 1 past the decimal. So it becomes 1821.6 pounds. I think I have 1 or 2 more. 2.030 milliliters minus milliliters, and I get this. That's what my calculator gives me. But notice this number goes to three decimal places. This goes to 3. So my answer has to go to 3, which means I have to tack a zero on there and make it 0.160 milliliters. The answers all reflect what was the least efficient tool you used in gathering your measurements. For that last one, both of them were really good tools. They went to 3 digits past the decimal on a milliliter scale, which is amazing. But your calculator kind of loses the precision there by ignoring that last zero, so we don't want to do that. So this brings us back to our original quandary. The first question was about that density. If I had a rock and it was 120.56 grams, I put water into a graduated cylinder and went to 70.1 milliliters. I dropped the rock in and went to 97.8 milliliters. I want to know what's the density. So I subtracted 2. Well, these both use the same exact tool that used 1 digit past decimal. So yes, my answer should have, for my subtraction, should have 1 digit past decimal. I take my density, I do my mass divided by volume, I get my number, and I need to report this. So this one has 5 sig figs. This one has 3 sig figs. So I would express this number as 4.35 grams per milliliter. So that's the end of this particular video. We will pick it up with dimensional analysis on the next one. Until then, toodles.